Today we're going to discuss the parametric and polar curves conic sections that pertains to the parametric equations, tangent lines, and arc lengths for parametric curve. In this discussion, we will study alternative ways of expressing curves in the plane. We will begin by studying parametric curves, which are the curves described in terms of the component functions. In this discussion, we will include methods for finding tangent lines to parametric curves. We will then introduce polar coordinate systems and discuss methods of finding tangent lines to polar curves, arc lengths for polar curves, and the areas enclosed by polar curves. So our attention will then turn into the review of basic properties of conic sections, such as the parabolas, the ellipses, and hyperbolas. And finally, we will consider conic section in the context of polar coordinate and discuss some of its application. So let's start with the parametric equations, tangent lines, and arc lengths for parametric curves. So the graph of the function must pass the vertical line test, a limitation that excludes curves with self-intersections or even such basic curves as circles. So in this discussion, we will study an alternative method for describing curves algebraically that is not subject to the severe restriction of the vertical line test. We will then derive formulas requiring to find slopes, tangent lines, and arc lengths for these parametric curves. We will conclude with an investigation of a classic parametric curve known as the cycloid. So let's start with the parametric equations. So you have here, suppose that a particle moves along a curve C in the xy plane in such a way that its x and y coordinate as functions of a time, which are the x is equal to f of t rather, and y equals to g of t. We call these the parametric equations of motion for the particle and refers to C as the trajectory of the particle or the graph of the equations. The variable is called a parameter rather, for the equation. Okay, so in this case, we can see here that you have a moving particle with a trajectory C. Okay, so let's have this one. Sketch that the trajectory over the time interval t is greater than or equal to 0 but less than or equal to 10 of the particle whose parametric equation of motion are x equals t minus 3 sine t and y equals 4 minus 3 cosine t. So one way to sketch the trajectory is to choose a representative succession of the time and then plot the xy coordinates of points on the trajectory and those time and connect the points with smooth curve. So the trajectory uh, will then be obtained in this way from a table of data. So in this case, we are going to make a table of data. You can use calculators, okay, to make a table of data. So for our solution, we are going to, since the restriction is the t is greater than or equal to 0 but less than or equal to 10, so we are going to substitute t, okay, by the numbers uh, from 0 to 10. So you have t, which is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then we also have the x. We are going to determine the x when we're going to substitute t by 0. So in this case, if t is 0, so you have 0 minus 3 sine 0, which is equal to, of course, 0. And then we are going to substitute t by 1. So 1 minus 3 sine 1, that is equivalent to, using your calculator, that's equal to negative 1.5. And here, that is equal to, round off, the 0, negative 0.7. And then you have 2.6. Okay, and then you have 6.3, and then you have 7.9 here, that is 6.8, and then you have 5, 8, that's 5 also, and then 9, that's 7.8, and then 10 would be 11.6. So if we are going to substitute these numbers to our equation, x is equal to t minus 3 sine t, these would be the values of our x. And then if we are going to determine the value of y using the values of 0 up to 10, okay, with the equation y is equal to 4 minus 3 cosine t. So using equation, so if this is 0, so cosine 0, that's equal to 1. Okay. And then if this is 1, so 4 minus 3 cosine 1, that's equal to, using your calculator, that is 2.4. Then here, that is 5.2. And then that is 7. This is 6. And then this is 3.1, 1.1, 7, that's 1.7. This is 4.4. This is 6.7, and you have 6.5. In other words, you have now you have now points. Okay, so your points are, you have 0, 1, then you have negative 1.5, 2.4, then you have negative 0.7, 5.2, and then you have 2.67, then you have 6.3, 6, and then 7.9, 3.1, then 6.8, 1.1, then you have 5, 1.7, then you have 5, 4.4, this is 4.4, then you have 7.8, 6.7, okay, and then you have 11.6, 6.5 rather, 6.5. Now we are going to plot these points in our coordinate system. So this would be, okay, the points. So that you have 0, 1, then you have negative 1.5, 2.4, and so on. So this would be the graph of the trajectory of the parametric equation with a time interval of t less than or equal, greater than or equal to 0, but less than or equal to 10. So although the parametric equations commonly arise in problems of motion with time as the parameter, they arise in this context as well. Thus, unless the problem dictates that the parameter t in the equation uh, x is equal to f of t, then y is equal to g of t, represent time, it should be viewed simply as an independent variable that varies over some interval of real numbers. In fact, there is no need to use the letter t for the parameter. Any letter not reserved for another purpose can be used. If no restrictions of the parameter are stated explicitly or implied by the equations, then it is understood that it is varies from negative infinity to positive infinity. So to indicate that the parameter t is restricted in the closed interval AB, we will write something like this. So you have x is equal to f of t, then we have y is equal to g of t with the interval that t is less than or equal to a but greater than wrong. T is greater than or equal to a but less than or equal to b. So this would be our interval. Okay. So let's have another example. Find the graph of the parametric equation x equals cosine t, y equals sine t in the interval t greater than or equal to 0 but less than or equal to 2 pi. Okay, so in this case, the solution for this one is um, find the graph. Okay, one way to find the graph is to eliminate the parameter t by noting that, okay, for our solution, clearly, since x is equal to cosine t and y is equal to sine t, and then the interval is t is greater than or equal to 0 but less than or equal to 2 pi, we have to take note that our x squared plus y squared can be written as sine squared t plus cosine squared t, which is equal to 1. Thus, the graph is contained in the unit circle x squared plus y squared equals 1. So, geometrically, the parameter t can be interpreted as the angle swept out by the radial line from the origin to the point uh, xy, which can be expressed as cosine t sine t on the unit circle. Okay, so if we are going to have the unit circle, so this would be the unit circle. So this one can be represented, this is just the same with cosine t sine t. Okay, um, as t increases from 0 to 2 pi, the point traces the circle counterclockwise starting at 1, 0. Okay, then when t is equal to 0 and completing one full revolution when t is equal to 2 pi. One can obtain different portions of the circle may vary by varying the interval over which the parameter varies. Okay, so this would be the graph of the parametric equation x is equal to cosine t, y is equal to sine t, where t is greater than or equal to 0 but less than or equal to 2 pi. So, for example, x is equal to cosine t, y is equal to sine t, where t is greater than or equal to 0 but less than or equal to pi, this represents the upper circle of these of this graph. Okay, so let's have orientation. The direction in which the graph of a pair of parametric equation is traced as the parameter increases is called the direction of the increasing parameter, or sometimes the orientation imposed on the curve by the equation. Thus, we make a distinction between the curve, which is a set of points, and the parametric curve, which is a curve with an orientation imposed on it by a set of parametric equation. Um, for example, uh, we have here the graph, okay, that the circle represents parametrically, okay, is traced counterclockwise as t increases, and hence the counterclockwise orientation. Okay, now if you can notice, okay, on the graph previously presented in the other slide, the orientation of the parametric curve can be indicated by arrowhead. So to obtain the parametric equation of the unit circle with counterclockwise orientation, we can replace t by negative t. Okay, and use the identities cosine negative t is equal to cosine t, and sine negative t is equal to negative sine t. So this yields that you have uh, x equals cosine t, y equals negative sine t, as t is greater than or equal to 0 but less than or equal to 2 pi. Okay, so here in this parametric equation, the circle is traced clockwise by a point that starts at 1, 0 when t is equal to 0, and completes one full revolution when t is equal to 2 pi, okay, which is represented by this circle. Okay, so let's have this example. Graph the parametric curve x is equal to 2t minus 3, y equals 6t minus 7 by eliminating the parameter, and indicate the orientation of the graph. So for our solution for in this case, to eliminate the parameter, we will solve the first equation for t as a function of x. Then substitute this expression for t into the second equation. So you have t is equal to, okay, as we have here, 1/2 times you have x plus 3. Okay. And then you can now solve for y, which is equal to 6 1/2 times x plus 3 minus 7. Simplify, y is equal to, you have 3x plus 2. So the graph is a line of the curve 3 and y-intercept 2. So to find the orientation, we must look to the original equation. The direction of increasing t can be deduced by observing that x increases as t increases, or by observing that y increases as t increases. So either piece of information tell us that the line is traced left to right. So this would be the equation. This would be the equation of the line with the orientation. Okay, so let's have expressing ordinary functions parametrically. So an equation y equals f of x can be expressed in a parametric form by introducing the parameter t equals x. This yields the parametric equation x equals t, equals t, y equals f of t. So for example, the portion of the curve, you have y equals cosine x, let's say cosine x, over the interval negative 2 pi, close interval negative 2 pi, 2 pi rather, can be expressed parametrically as uh, x equals t, y equals cosine t in the interval t greater than or equal to negative 2 pi, but less than or equal to 2 pi. Okay, so the graph of these uh, parametric equation would be this one, okay, in the blue traced. Okay, so if a function f is 1 to 1, then it has an inverse function f raised to negative 1. In this case, the equation y, let's say you have y equals the inverse of f of x is equivalent to x is equal to f of y. Okay, we can express the graph of the inverse of f in a parametric form by introducing the parameter y equals t. This yields the parametric equation. You have x is equal to f of t, y is equal to t. So for example, we have here the graph. Okay, you have this one is equal to the equation f of t here. F of x is equal to, let's say that's x to the fifth plus x plus 1. Okay, and its inverse. The graph of the function can be represented parametrically as x equals t, y equals t squared plus t plus 1. And the graph of the inverse can be represented parametrically as uh, x is equal to, you have t raised to 5. By the way, this is not squared, that must be 5, plus uh, t plus 1, y equals 1. Let me check this one first. It must be equal to 5. Okay. So let's have tangent lines to parametric curves. We will be concerned with the curves that are given by a parametric equation: x is equal to f of t, y is equal to g of t, in which f of t and g of t has continuous first derivatives with respect to t. Uh, it can be proved that if dx over dt is equal to 0, when then y is a differentiable function of x. In which case the chain rule implies that dy over dx is equal to dy over dt all over dx over dt. So okay, this formula makes it possible to find dy over dx directly from the parametric equation without eliminating the parameter. Okay, so let's have an example. Find the slope of the tangent line of the unit circle x is equal to cosine t, y is equal to sine t, where t is less than or equal to where t is greater than or equal to 0 but less than or equal to 2 pi, at the point where t is equal to pi over 6. So you have here the circle, and you have the pi over 6, the angle, and then you are going to determine the tangent line. So in this case, to solve this case, we are going to use the concept that is presented in the previous slide, that dy over dx is equal to dy over dt over dx over dt. So in this case, since we have x is equal to cosine t and y is equal to sine t, dy over dt, we are going to get the derivative of the first derivative of our y, which is equal to cosine t. And then the derivative of our x would be, you have negative sine t, which is, this can be, this is actually the identity of negative cotangent t. Thus, the slope of the t, so the slope of the t, okay, the slope at t rather, is equal to uh, pi over 6. We could have the solution for that, that our dy over dx, okay, where t is equal to pi over 6, can be expressed as negative cotangent pi over 6, which is, using the calculator, or this is actually as a special angle, the negative cosine pi over 6 is equal to negative square root of 3. So in other words, the slope is equal to negative square root of 3. Okay. So it follows that the formula, so this formula, okay, that the tangent line is a parametric curve with will be the horizontal at those points where dy over dt is equal to 0 and dx over dt is not equal to 0. Since dy over dt is equal to 0 at such points, so two different situation occurs when dx over dt is equal to 0. At points where dx over dt is equal to 0 and dy over dt is not equal to 0, the right side of this equation, okay, okay, has a non-zero numerator and a zero denominator. Okay, we will agree that the curve has infinite slope and a vertical tangent line at such points. The points where dx over dt and dy over dt are both zero, the right side of this equation, you have dy over dx of that's equal to dy over dt over dx over dt, okay, becomes an indeterminate form. We call such points singular points. No general statement can be made about the behavior of the parametric curves at singular points. They must be analyzed case by case. Okay, so let's have this example. In the disastrous first flight, an experimental airplane follows a trajectory of the particle x equals t minus 3 sine t, y equals 4 minus 3 cosine t, where t is greater than or equal to 0. Okay, so but in this, it should be, according to the illustration, it crashes into a wall at t is equal to 10. Okay, so based on this illustration, as we can see here, as t equal to 10, the paper plane, okay, hit the wall. Okay, so at what times was the airplane flying horizontally? So that is the problem. So for our solution, the airplane was flying horizontally at those times when dy over dt is equal to 0. So you have dy over dt is equal to 0, and you have dx over dt is not equal to 0. From the given trajectory, we have dy over dt. So in this case, our dy over dt would be equal to 3 sine t. And for our dx over dt rather, is equal to 1 minus cosine t. So setting dy over dt equals 0 yields the equation 3 sine t is equal to 0. Or more simply, sine t is equal to 0. So this equation has four solutions. So take note, by this, we could say that 3 sine t is equal to 0, in which sine t is equal to 0, which has four solutions, okay, when t is greater than equal to 0 but less than or equal to 10. So t is equal to 0, t is equal to pi, t is equal to 2 pi, and you have t is equal to 3 pi. So dx over dt is equal to 1 minus uh, cosine t, it's not equal to 0. For these values of t, the airplane was flying horizontally at t equals 0. So this is t is equal to approximately equal to, since pi, that's 3.14. And then since this is 2 pi, so t is approximately equal to 6.28. And in this case, our t is approximately equal to 9.42. Okay, so that is the times, okay, where the airplane fly horizontally. So same equation, same problem, but in this case, at what times was it flying vertically? So in this case, it was then asked if uh, if it flown vertically. Okay. So for the solution, the airplane was flying vertically um, at those times when dx. So when you have uh, dx over dt is equal to 0, and our dy over dt should not be equal to 0. So setting dx over dt equals 0, this yields the equation. So our equation must be 1 minus 3 cosine t, which is equal to 0, or, okay, simply cosine t is equal to 1/3. So this equation has three solutions. In the time interval, t is greater than or equal to 0 but less than or equal to 10. So our t here would be uh, the arc cosine 1/3. Then we also have t is equal to 2 pi minus arc cosine 1/3. And then the other one is you have uh, 2 pi plus cosine arc cosine 1/3. So since this would be dy over dt equals 3 cosine t is not 0 at these points, it follows that the airplane was flying vertically, okay, at t is approximately equal to, using your calculator, that's equal to 1.23. This is t is approximately equal to 5.05, and this one t is approximately equal to 7.51, which again is consistent to the graph. Okay, this is the graph. Okay, so let's have this one. The curve represented by a parametric equation x is equal to, this must be t squared, not t2. T squared, and this is t cubed. Okay, where t is greater than negative infinity but less than positive infinity. Okay, is called semicubal parabola. The parameter t can be eliminated by cubing x and squaring y, from which it follows that y squared is equal to x cubed. Okay, so the two branches meet at the origin as presented in the equation, in the graph rather, okay, which corresponds to t is equal to 0 in the parametric equations. So this is a singular point because the derivatives dy over dt is equal to 2t and dy over dt is equal to 3t squared are both 0 there. Okay, so let's have arc length of the parametric curves. Mhm. So arc length of parametric curves. So we have here the following uh, results provides the formula for finding the arc length of the curve from the parametric equation of the curve. So its derivation is similar to the formula. Uh, you have x equals cosine t, y is equal to sine t, where t is less than or equal to 0, but where t rather is greater than or equal to 0, but less than or equal to pi. Okay, so we have here the arc length formula for the parametric curve. If no segment of the curve represented by the parametric equation x is equal to x of t and y is equal to y of t, where t is greater than or equal to a but less than or equal to b, is traced more than once as t increases from a to b, and if dx over dt and dy over dt are continuous functions for t greater than or equal to a but less than or equal to b, then the arc length L of the curve is given by the formula L is equal to the integral of the square root of the uh, the squared quantity of dx over dt plus the squared quantity of dy over dt, dt from A to B. Okay, so let's have this uh, example. Okay, so find the circumference of the circle of the radius A from the parametric equation. X is equal to A cosine t, y equals A sine t, t is greater than equal to 0 but less than equal to 2 pi. Okay, so for our solution in this case, so the formula is L is equal to the integral of the square root of the squared quantity of dx over dt plus the squared quantity of dy over dt, okay, from 0 to 2 pi. So in this case, this is actually the integral from 0 to 2 pi, which is equal to the square root of negative a sine t quantity squared plus you have a cosine t quantity squared dt. So in this case, you have from 0 to 2 pi. So this is actually the this one that is can be simplified as a dt. Okay, a dt. Okay, which is equal to the at, okay, from 0 to 2 pi, which is actually equal to 2 pi a. So that is our answer. So the circumference of the circle, okay, of the radius a from the parametric equation x is equal to a cosine t, y is equal to a sine t, where t is greater than equal to 0 but less than equal to 2 pi, is equal to 2 pi a, not d, that it must be a. Sorry. Let's change this one into a. Okay. So let's this one, the cycloid, which is also known as the apple of this curve. Okay. The result of this discussion can be used to investigate a curve known as cycloid. This curve, which is one of the most significant in the history of mathematics, can be generated by a point on the circle that rolls along the straight line. So this one, this one. Okay. This curve has a fascinating history, which we are going to have it shortly. But first, we will show how to obtain the parametric equation for it. For this purpose, let us assume that the circle has the radius a and rolls along the positive x-axis in the rectangular coordinate system. So let P, okay, a point xy, be a point on the circle that traces the cycloid, and assume that P is initially at the origin. We will take we will take as our parameter the angle theta and is swept out by the radial line to P as the circle rolls. So which is actually represented with the illustration that I've enclosed. So the motion of P is the combination of the movement of the circle's center parallel to the x-axis and the rotation of P about the center. So as the radial line swept out an angle theta at point P traverses an arc on of the length a theta. and the circle moves a distance a theta along the x-axis. Therefore, as suggested with this figure, the center moves to the point. Okay, so the point, it moves to the point uh, a theta a, and the coordinates of the p. So the coordinates of the p, okay, would be, you have the x must be equal to a theta minus a, it must be minus a sine theta, and our y is equal to a minus a cosine theta. Okay, so these are the equations of the cycloid in terms of the parameter theta. One of the reasons the cycloid is important in the history of mathematics is that the study of its properties helped to spur the development of early versions of differentiations and integration. So the work of cycloid was carried out by some of the most famous names in 17th century mathematics, which includes Johann and Jacob uh, Bernoulli, okay, or Bernoulli, okay, Descartes. We also have the Descartes. We have also El Hospital, Newton, and Leibniz. So the curve was named the cycloid by the Italian mathematician, okay, and astronomer Galileo, who spent over 40 years investigating its properties. An early problem of interest was that of constructing tangent line to the cycloid. This problem was first solved, of course, by Descartes and then by Fermat, whom Descartes had challenged with the question. The modern solution of this problem follows directly from the parametric equation, which is the parametric equation is x is equal to a theta minus uh, a sine theta, then y is equal to a minus a cosine theta. Okay. Um, and of course, the formula dy over dt, which is equal to dy over dt all over dx over dt. So for example, using the formula dy over dx is equal to dy over dt over dx over dt, it is a straightforward to show that the x-intercepts of the cycloid are copes and that there is the horizontal tangent line to the cycloid halfway adjacent to x-intercept. Okay, so another early problem was determining the arc length of an arch of the cycloid. This was solved in 1658, yes, 1658 by the famous British architect and mathematician Sir Christopher Wren, WREN. Okay, he shown that the arc length of one arch of the cycloid is exactly 8 times the radius of the generating circle. So the cycloid is also important historically because it provides the solution of two famous mathematical problems: the the branchitron, uh, branchitochrone. The spelling is this one, branchitochrone. So here you have the uh, branchitochrone tochrone problem, okay, which is taken from the Greek word meaning shortest time. And we also have the tautocron, tautocron, okay, tautocron problem, which means equal time. The branchitochrone problem is to determine the shape of the wire along which a bead might slide from a point P to another point Q, not directly below in the shortest time. The Tautocron problem is to find the shape of the wire from P to Q such that two beads started at any point on the wire between P and Q reach Q at the same amount of time. So the solution of both problems turns out to be inverted cycloid. Um, Another in June of 1969, 1696 rather, 1696, Johann Bernoulli or Bernoulli rather uh, posed the Branchet-Tocron problem in the form of a challenge to another mathematician. At first, one might conjecture that the wire should form a straight line, since the shape results to the shortest distance from P to Q. Um, However, the inverted cycloid allows the beads to fall more rapidly at first, building up sufficient speed to reach Q in the shortest time, even though it travels a longer distance. The problem was solved by Newton's, Leibniz, and El Hospital, as well as Johann Bernoulli and his older brother Jacob. It was formulated and solved incorrectly years earlier by Galileo, who thought that the answer was a circular arc. In fact, Johann was so impressed with his brother Jacob's solution that he claimed it as his own, which is this is just this was just one of many disputes about the cycloid that eventually lead to the curve being known as apple of discord. Okay, one solution of the um, bronchitochrone problem leads to the differential equation. We have this famous differential equation. Okay, so this one of the famous differential equation. I'm going to write it here. So you have 1 plus dy over dx quantity squared y is equal to 2a, where a is a positive constant. We leave it as we are going to have that only that portion. Okay, so that ends the presentation.